At the International Rice Research Institute in Los Banos, near Manila, and in its local branches in the principal rice-growing regions, the race against time to carry out this task has long been underway. The starting point is the Institute's World Rice Seed Bank, which has the biological genotype of 120,000 rice varieties from all regions where rice is grown. This was where the genetic potential came from for the highly productive varieties used in the first phase of the Green Revolution, which has become the spearhead of the fight against hunger in Asia, albeit with copious use of modern agricultural technology. The seeds to rebuild rice cultures in countries like Cambodia, where they'd been completely destroyed in the devastation of war, also came from here. Today, development work on endowing new varieties with lasting powers of resistance against the most important types of stress is seen as just as vital as attaining bigger yields. This applies both to conventional breeding and to what goes on in the genetic laboratories. Here's biogeneticist Rebecca Nelson.
For blast and bacterial blight, two of the very most important diseases of rice, there are many resistance genes, either in cultivated rice or in the wild relatives of rice. And we would like to use DNA markers or little flags composed of genetic material to help us make use of these resistance genes more effectively. While there are many resistance genes, the problem has been that resistance has been frequently unstable. So a resistant cultivar in the farmer's field may very soon be overwhelmed by disease because the pathogen has evolved so that it can now overcome what was previously an effective form of resistance. We believe in our intelligence with that. The other strategy is to study the genetics of resistance of traditional cultivars. So traditional cultivars, for instance, from Africa that have been able to resist the blast fungus for many decades, or for many years at least. And so we feel that by understanding the genetics of resistance in these traditional cultivars and then bringing those gene combinations into new cultivars with better yield, that then we can really probably stabilize resistance to the pathogen.
Systematic attempts to breed varieties which combine at least some of the desired characteristics have been going on for some time now. More and more new varieties are being created for cultivation under all sorts of conditions. Rice for the future. Once a rice has passed the test here, it still has to be adapted to conditions in the regions. It's a lengthy process. And what's been the success so far? Dr. Gurdev Kush, head of the Institute's rice breeding program, takes a positive view.
Here is a plant of IR64, which is a very widely planted modern variety. It has small panicles and rather weak stems. It yields about 50% grain, 50% leaves and stems. The new variety which we are trying to produce has large number of grains, very large panicles. It has thick stems so that it does not fall over when these grains are maturing. In this plant, about 60% will be grain and 40% leaves and stem. So this will produce 25 to 30% more grains as compared to the modern high-yielding varieties. And it should do so without the need for additional chemical inputs. Because it has thick and deep roots, it should be able to get additional nutritional elements from the deeper layers of the soil. We are also trying to incorporate genes for resistance to the diseases and insects so that it will not require chemical inputs because it has the genetic resistance to the major diseases and insects.
In the area around Los Banos, agricultural implements and threshing machines are being built by private workshops to designs produced by technicians at the Rice Institute. The idea is to make up for the increasing shortage of agricultural labourers by simplifying work for farmers. Here, the good-natured carabao has already become redundant, but this field belongs to a landowner who can afford the costs of mechanisation. A seed carpet like this is intended to simplify the work of transplanting the young plants into the open field. Up to this point, they're usually grown in seed beds. Rice cultivation, as it's traditionally been practiced here, is the most labour-intensive form of cereal production there is. Per hectare, some 250,000 seedlings have to be transplanted, an 8-hour day's work for 20 to 30 people. Altogether, in the course of a cultivation season, from ploughing to when the harvest is carted away, every hectare requires up to 1,000 hours of work. Painstaking attempts are also being made to find ways of combating the rat nuisance. But in view of the precarious economic situation of most rice farmers, it seems rather unlikely that the solution for the future will lie in plastic fences like the one here. Rat poison is no solution either, because in many parts of Asia, people like to eat rats. Once it's been threshed and the husks removed, rice is less trouble to prepare than any other cereal. That's one of the reasons the people in the tropical regions of Asia have never bothered with bread. It's estimated that the worldwide requirement around the year 2020 will be 760 million tons of rice per year, 60% more than the roughly 460 million it is today. By then, the number of rice eaters will be equal to today's entire world population. Nearly all of them will be inhabitants of the Third World, where 80% of all the poor already live. Whether Asian rice farmers will succeed in meeting the extra demand doesn't just depend on more productive, less stress-endangered varieties of rice and more rationalized cultivation and harvesting methods, though. Also needed are a suitable market framework and land reforms. Those who don't own the land they cultivate and are struggling to make ends meet will continue to make do with such necessities as they can afford. Enough rice for Asia in the year 2020. We know what the objective is, but time is pressing and there's still a long, laborious road ahead.